Every morning at dawn, something ancient stirs inside your Labrador. Before you hear the alarm, before the first car engine turns over in your neighborhood, Boni's body has already begun its orchestrated transition from
You're
sleep to
such a good boy.
wakefulness.
Ready
This
for
is
a
not
walk?
learned
Let's
behavior.
go, buddy.
This is biology written over
Good boy, go
40,000
fetch.
years of
Come
evolution.
here, buddy.
A genetic inheritance from wild canines, who survived because their internal clocks could predict the arrival of light with extraordinary precision. When gray wolves roamed the forests and tundra that covered much of the northern hemisphere, survival depended on synchronization with the sun. The wolf that woke too early wasted precious energy in the darkness. The wolf that woke too late missed the optimal hunting window when prey animals moved between sleeping and feeding grounds. Natural selection favored animals whose physiology could anticipate environmental changes. And over countless generations, this pressure sculpted an internal timing system of remarkable sophistication. Your Labrador carries this same biological architecture, despite living in a world radically different from the one that shaped it. The moment light enters Boni's eyes each morning, a cascade of neurological events begins in a structure buried deep in the brain called the suprachiasmatic nucleus. This cluster of approximately 20,000 neurons, positioned just above the point where the optic nerves cross, functions as the master clock that governs nearly every time-dependent process in your dog's body. The suprachiasmatic nucleus is not simply responding to light, it is interpreting it, using the information to synchronize thousands of downstream biological processes that must occur in precise temporal order for your dog to function optimally. What makes this system remarkable is its autonomy. Even in complete darkness, isolated from all environmental cues, the suprachiasmatic nucleus continues to generate rhythmic signals, with a period close to 24 hours. Scientists have demonstrated this by surgically removing the suprachiasmatic nucleus from laboratory animals and keeping the tissue alive in culture dishes, where individual neurons continue to fire in rhythmic patterns for weeks. This intrinsic timekeeping ability means that Boni's internal clock doesn't require light to function, but it absolutely requires light to remain synchronized with the external world. Without regular light exposure, the clock drifts, running slightly longer than 24 hours and gradually falling out of alignment with day and night. The pathway through which light reaches this master clock is surprisingly direct. Specialized cells in your Labrador's retina, distinct from the rods and cones that create visual images, contain a photopigment called melanopsin. These cells are exquisitely sensitive to blue wavelength light around 480 nanometers, the color that dominates the sky during daylight hours. When dawn light strikes the retina, melanopsin-containing cells fire signals that travel along the retino-hypothalamic tract straight to the suprachiasmatic nucleus, bypassing the visual processing centers entirely. This is why even dogs with severe visual impairment can maintain normal circadian rhythms. They don't need to see the light, they only need to detect it. The suprachiasmatic nucleus uses this morning light signal to coordinate an enormous number of physiological processes. Within 30 minutes of light exposure, Boni's adrenal glands begin secreting cortisol, the hormone that mobilizes energy and promotes wakefulness. Body temperature, which dropped during the night to conserve energy, begins rising toward its daytime peak. Digestive enzymes increase in preparation for food intake. Blood pressure elevates. Even the expression of genes within individual cells throughout the body shifts into daytime mode. A molecular changing of the guard that happens in liver cells, muscle cells, fat cells, and nearly every other tissue type simultaneously. This coordination is essential because biological processes are deeply interdependent. Consider glucose metabolism. Your Labrador's body handles sugar differently at different times of day, with insulin sensitivity highest in the morning and declining toward evening. This circadian variation in metabolic function reflects an evolutionary adaptation. Wild canines are typically fed after successful hunts in the early morning or late afternoon, and their metabolism evolved to expect nutrient intake during these windows. When Boni eats at the optimal circadian time, nutrients are efficiently processed and stored. When feeding occurs at the wrong circadian phase, the same meal produces higher blood sugar spikes and less efficient energy storage, a phenomenon that has been documented across numerous mammalian species. Sleep itself is not a single uniform state, but rather a complex architecture of distinct stages that cycle throughout the night. When Boni falls asleep, they do not immediately enter deep unconsciousness. Instead, they progress through a sequence that begins with light drowsiness, advances into deeper non-dreaming sleep, and eventually reaches rapid eye movement sleep, where vivid dreams occur. Each complete cycle lasts approximately 20 minutes in dogs, much shorter than the 90-minute cycles humans experience, meaning your Labrador transitions through these stages many times each night. The deepest stage of non-dreaming sleep, characterized by large, slow brainwaves, serves critical restorative functions. During these periods, the pituitary gland releases pulses of growth hormone that stimulate tissue repair and muscle development. Cerebrospinal fluid flows more freely through the brain, washing away metabolic waste products that accumulated during waking hours, including proteins associated with cognitive decline. The immune system ramps up production of infection-fighting cells. This is not passive rest, it is active biological restoration, and its timing and depth are directly controlled by the circadian system. Rapid eye movement sleep, the stage where dreaming occurs, serves equally important but different functions. During REM periods, the brain shows activity patterns remarkably similar to wakefulness. Yet the body remains paralyzed, except for the eyes and respiratory muscles. This is when memories consolidate, when the experiences of the previous day are processed and integrated into long-term storage. Research has shown that dogs deprived specifically of REM sleep struggle to learn new tasks and retain training, suggesting that the commands you practice with Boni during the day are neurologically cemented during REM periods at night. Emotional regulation also depends heavily on REM sleep, with disrupted REM leading to increased anxiety and reduced stress resilience in multiple mammalian species. The circadian system doesn't just determine when sleep occurs, it profoundly influences the quality and structure of sleep itself. The propensity for deep slow-wave sleep follows a circadian pattern, reaching maximum depth during the biological night, as determined by the suprachiasmatic nucleus. Similarly, REM sleep is most abundant in the late night and early morning hours, reflecting an ancestral pattern where wild canines would experience their deepest dreaming sleep in the pre-dawn darkness, when the circadian system is misaligned, when the master clock indicates a different time than the external environment. These carefully orchestrated sleep stages become disrupted and fragmented. The transformation from wilderness to living room has created a profound mismatch between your Labrador's biology and their environment. Wild canines experienced extraordinarily predictable light patterns, brilliant full-spectrum sunlight during the day, with intensities reaching 100,000 lux, complete darkness at night broken only by moonlight, which contains virtually no blue wavelengths, and gradual twilight transitions that provided clear biological signals for activity changes. Modern indoor living inverts this pattern almost completely. Indoor lighting rarely exceeds 500 lux, far below the threshold needed to robustly entrain circadian rhythms. Yet this dim light persists late into the evening, rich in the blue wavelengths that most powerfully signal daytime to the suprachiasmatic nucleus. The shift to LED lighting technology, which has dominated residential and commercial spaces by 2026, has amplified this problem considerably. Unlike incandescent bulbs, which produce warm orange and red light with minimal blue content, LED fixtures emit substantial energy in the blue spectrum because of the way they generate white light. To the melanopsin-containing cells in Boni's retina, the LED bulb, illuminating your living room at 9 in the evening, is neurochemically indistinguishable from morning daylight. The suprachiasmatic nucleus receives the signal to maintain daytime physiology, suppressing melatonin production and maintaining alertness. Even as homeostatic sleep pressure, the biological drive to sleep that builds with every hour awake, simultaneously increases. Understanding this mismatch reveals why so many modern dogs exhibit sleep problems that were virtually unknown in their wild ancestors. Restlessness, difficulty settling at night, frequent waking, and anxiety behaviors in the evening hours are not character flaws or training failures. They are predictable biological responses to an environment that sends conflicting signals to an ancient timing system. Boni's body is trying to maintain a 24-hour rhythm, designed for the savanna and forest, while living in conditions that resemble perpetual twilight. Never quite bright enough to fully activate daytime physiology, never quite dark enough to permit complete nighttime restoration. The implications extend far beyond simple sleep quality. Every major physiological system in your dog's body operates on circadian schedules coordinated by the suprachiasmatic nucleus. Immune function fluctuates across the day, with different components of the immune system more or less active depending on circadian phase. Metabolism shifts between anabolic and catabolic states according to time of day. Even DNA repair mechanisms in individual cells follow circadian patterns. When the master clock that coordinates all these systems receives corrupted timing information from inappropriate light exposure, the result is internal desynchronization. Different organ systems operating on different schedules, a physiological state analogous to permanent jet lag. Research measuring biological markers of circadian timing has revealed just how plastic and vulnerable this system is to environmental influence. The timing of melatonin secretion, one of the most reliable indicators of circadian phase, can shift by several hours, depending on recent light exposure history. Dogs exposed to bright light in the evening show melatonin onset occurring significantly later than dogs kept in dim amber light during the same period. This demonstrates that the circadian system is not rigidly fixed but rather continuously adjusting itself based on the environmental signals it receives. This plasticity was adaptive in the ancestral environment where seasonal changes in day length required gradual adjustments to activity patterns. But it becomes a vulnerability in modern environments where light patterns bear no relationship to natural cycles. The path forward requires recognizing that your Labrador is not a machine independent of environmental context, but rather a biological organism whose fundamental physiology evolved under specific conditions. Boni's health, behavior, cognitive function, and longevity are intimately tied to the alignment between internal circadian biology and external light environment. The chapters ahead will translate this scientific foundation into practical protocols, examining precisely how blue light disrupts melatonin production, quantifying the specific timing and intensity of light exposure needed to properly entrain the circadian system, and providing actionable guidance for optimizing your home lighting to support rather than undermine your dog's biological needs. This is not lifestyle optimization for its own sake, it is the foundation upon which every other aspect of your Labrador's health depends. The LED bulb in your living room is lying to Boni's brain. At 10 o'clock on a winter evening, when ancestral canines would have been experiencing absolute darkness for hours, that innocent-looking fixture is broadcasting a neurochemical message indistinguishable from midday sun. The photoreceptors in your Labrador's eyes cannot tell the difference between the blue wavelengths emitted by your ceiling lights and the blue wavelengths that flood the sky at dawn, and this deception triggers a cascade of hormonal disruptions that undermine every aspect of your dog's health. Melatonin is often misunderstood as simply a sleep hormone, something that makes you drowsy when it appears in the bloodstream. This characterization misses the profound scope of what melatonin actually does. Synthesized in the pineal gland, a small endocrine structure deep in the brain, melatonin serves as the primary hormonal messenger that communicates nighttime information to every cell in your dog's body. When melatonin levels rise in the evening, they signal to the liver, the muscles, the immune system, the digestive tract, and thousands of other tissues that the active phase of the day has ended and the restorative phase has begun. Melatonin doesn't simply cause sleep, it orchestrates the entire constellation of physiological changes that define biological night. The production of melatonin follows a precise biochemical pathway that is exquisitely vulnerable to light exposure. During daylight hours, the suprachiasmatic nucleus actively suppresses melatonin synthesis, keeping the pineal gland shut down even though it possesses all the molecular machinery needed to produce the hormone. As evening approaches in natural conditions, as the sun dips below the horizon and blue wavelengths disappear from the sky, the suprachiasmatic nucleus gradually releases this inhibition. The pineal gland begins converting serotonin, a neurotransmitter, into melatonin through a two-step enzymatic process. Under optimal conditions in dogs, melatonin concentrations begin rising approximately 2 hours before habitual sleep time, reach peak levels in the middle of the night, and fall rapidly in the hours before dawn. This timing is not arbitrary. The gradual rise of melatonin in the evening creates what researchers call the biological twilight, a transitional period during which body temperature begins dropping, alertness gradually wanes, and the brain shifts from daytime to nighttime mode. This transition requires time, it cannot happen instantaneously. When melatonin onset occurs at the proper circadian phase, Boni experiences a smooth glide path into sleep, a gentle physiological descent that allows all the preparatory processes to unfold in proper sequence. When melatonin onset is delayed or suppressed, sleep becomes an abrupt transition that the body struggles to navigate. Like trying to land an aircraft without a proper approach, the sensitivity of this system to light is startling in its precision. Research measuring melatonin suppression across different wavelengths of light has revealed that blue light, around 480 nanometers, is approximately 5 times more effective at inhibiting melatonin than longer wavelength red or amber light of equal intensity. This spectral sensitivity reflects the tuning of melanopsin photoreceptors in the retina, which evolved to detect daylight and communicate that information to the circadian system. A study published in the Journal of Clinical Endocrinology and Metabolism demonstrated that exposure to just 40 lux of blue-enriched light, roughly equivalent to a moderately bright smartphone screen, can suppress melatonin production by 50% in mammals. Meanwhile, the amber light at 200 lux, 5 times brighter, produces virtually no suppression at all. Walk through your home at 9 in the evening and catalog the blue light sources surrounding your Labrador. The overhead LED fixtures, marketed as daylight or cool white, typically emit substantial energy in the 450 to 490 nanometer range. The television screen, the tablet someone is using on the couch, the LED strips under the kitchen cabinets, the digital clock displays, and the charging indicators on various devices each contribute to an aggregate blue light exposure that keeps Boni's pineal gland locked in daytime mode. Studies measuring light intensity in modern homes have found that the average evening illumination has increased by approximately 300% since the year 2000. Driven almost entirely by the transition to LED technology and the proliferation of backlit screens. The consequences of this chronic evening light exposure extend far beyond delayed sleep onset. When melatonin production is suppressed night after night, the effects accumulate across multiple physiological systems. Melatonin is a potent antioxidant that neutralizes free radicals, highly reactive molecules that damage cellular components, including DNA, proteins, and lipid membranes. During normal nighttime hours when melatonin concentrations are high, this antioxidant protection is at its peak, allowing cells to repair the oxidative damage accumulated during the metabolically active daytime hours. When melatonin is chronically suppressed, this repair window shrinks, and oxidative stress accumulates progressively. The immune system depends heavily on the circadian regulation of melatonin. Multiple types of immune cells possess melatonin receptors, and their function varies dramatically depending on whether melatonin is present or absent. Natural killer cells, which patrol the body searching for infected or cancerous cells, show peak activity during the high melatonin phase of the night. Inflammatory cytokines, signaling molecules that coordinate immune responses, follow circadian patterns that are directly influenced by melatonin timing. Studies in multiple mammalian species have demonstrated that chronic circadian disruption, particularly when involving suppressed melatonin, leads to measurably reduced immune function and increased susceptibility to infections. For your Labrador, this translates into longer recovery times from illness, increased vulnerability to pathogens, and accelerated immune system aging. The metabolic consequences of disrupted melatonin are equally profound. Melatonin receptors are expressed in adipose tissue, pancreatic cells, liver cells, and skeletal muscle, the major organs involved in energy metabolism. When melatonin levels rise normally in the evening, they signal these tissues to shift from energy expenditure mode to energy conservation and restoration mode. Insulin sensitivity decreases in preparation for the fasting period of sleep. Glucose production by the liver ramps down. Fat cells become less responsive to signals promoting fat breakdown. These metabolic adjustments are appropriate for the inactive nighttime period and help maintain stable blood sugar during the hours without food intake. When evening light exposure suppresses melatonin, the metabolic confusion that results can be measured in laboratory tests. Studies examining metabolic function in animals exposed to light at night have documented elevated nighttime blood glucose, increased insulin resistance, and altered lipid metabolism compared to animals kept in natural nights. Over time, this metabolic disruption manifests as weight gain, decreased lean muscle mass, and increased visceral fat accumulation. the deep abdominal fat that produces inflammatory signaling molecules. For Labradors, a breed already prone to weight management challenges, chronic melatonin suppression removes one of the body's natural regulatory mechanisms that helps maintain healthy body composition. Perhaps most visible to dog owners are the behavioral manifestations of disrupted melatonin patterns. Melatonin influences the function of brain regions involved in emotional regulation, particularly the amygdala, which processes fear and anxiety responses. Under natural conditions, rising melatonin in the evening promotes a sense of calm and reduces reactivity to stressors. An adaptive response that facilitates sleep in an environment where vigilance is needed to decrease during vulnerable nighttime hours. When melatonin onset is delayed by light exposure, this evening calmness never fully develops. Boni remains in a state of heightened alertness, where normal household sounds and activities that should be ignorable instead trigger arousal and attention. Owners often describe this as evening restlessness or second wind behavior. Boni paces, seeks attention, reacts to minor stimuli, and resists settling despite appearing physically tired. This is not willful misbehavior or insufficient exercise. It is the predictable behavioral output of a neurochemical system that is receiving conflicting signals. The homeostatic sleep drive, the biological pressure to sleep that builds with time awake, is increasing and generating fatigue. Simultaneously, the suppressed melatonin and elevated cortisol maintained by evening light exposure are promoting wakefulness and vigilance. The dog exists in an uncomfortable middle state, too tired to be fully engaged but too neurochemically activated to relax into sleep. The development of this condition follows a pattern that makes it particularly insidious. Unlike acute disruptions that produce immediate, obvious consequences, chronic evening light exposure creates a gradually worsening baseline that owners often fail to recognize as abnormal because the deterioration is so slow. In the first weeks, Boni might show only subtle changes, taking slightly longer to settle in the evening, waking once or twice during the night instead of sleeping through. These changes are easily dismissed as random variation. Over months, the sleep fragmentation increases, the evening restlessness becomes more pronounced, and secondary effects begin appearing, such as reduced trainability, increased anxiety during separation, decreased frustration tolerance, and changes in appetite patterns. By the time owners recognize these as problems requiring intervention, the circadian system may have been operating in a disrupted state for many months or even years. The suprachiasmatic nucleus has effectively learned an incorrect schedule, one where evening light exposure has pushed the entire circadian phase later and later. The melatonin onset that should occur at 8 in the evening might not happen until 11 or midnight. The timing of minimum body temperature, normally occurring in the pre-dawn hours, shifts into early morning. The cortisol awakening response, which should produce a sharp rise in alertness shortly after dawn, becomes blunted and delayed. The entire temporal architecture of physiology has been reconstructed around an artificial light-dark cycle that bears no relationship to the solar day. Research using continuous measurement devices to track circadian markers in household dogs has revealed just how common this condition is. In one study examining over 200 dogs living in typical urban and suburban homes, fewer than 20% showed melatonin onset timing that fell within the range observed in dogs housed outdoors with natural light exposure. The majority showed delays of 2 to 4 hours, with some extreme cases showing melatonin onset not occurring until after midnight despite the dogs being settled in darkened rooms. The correlation with evening light exposure was unmistakable. Homes with higher evening light intensities and greater use of blue-enriched lighting consistently produced dogs with more delayed and disrupted melatonin patterns. The tragedy of this situation is that both dogs and owners suffer needlessly from a problem that is entirely environmental and therefore entirely correctable. Boni's genes have not changed. The molecular machinery that generates circadian rhythms remains intact and functional. The suprachiasmatic nucleus is still capable of robust synchronization. The pineal gland can still produce abundant melatonin, and the downstream physiological systems are still prepared to respond appropriately to proper timing signals. What has changed is simply the light environment, and light environments can be modified with straightforward interventions that require no medication, no specialized equipment, and no fundamental lifestyle changes. Understanding the scope of the melatonin disruption crisis is not meant to generate anxiety or guilt but rather to establish the stakes clearly. Every evening that Boni spends under blue-enriched artificial light is an evening when their body is receiving incorrect temporal information. When melatonin production is being artificially suppressed, and when the cascade of nighttime restorative processes is being delayed or prevented. The accumulated effects of this chronic disruption manifest in reduced health span, the number of years your dog lives in a state of full vitality. This is not about adding years to life, although proper circadian function likely does that as well, but about ensuring that the years Boni does live are characterized by robust health, stable behavior, and optimal cognitive function rather than the gradual decline that chronic circadian disruption produces. The solution begins with morning light, and it must be delivered with an intensity and timing that most dog owners have never considered. When you take Boni outside at 7 in the morning for a brief bathroom break and then immediately return indoors, you have missed the single most powerful opportunity of the entire day to set their circadian system correctly. That 5-minute excursion, regardless of how bright the morning sun might be, is neurologically insufficient to provide the robust Zeitgeber signal that the suprachiasmatic nucleus requires to maintain proper synchronization. The ancestral pattern that shaped canine circadian biology involved hours of continuous outdoor exposure beginning at dawn. Wild canids did not experience a few minutes of bright light followed by immediate return to cave darkness. They remained in the outdoor environment throughout the entire morning period, exposed to progressively intensifying sunlight as the sun climbed higher in the sky. This extended exposure provided a powerful and unambiguous signal that reset the master clock with great precision each day. Modern indoor living inverts this pattern almost completely. We provide brief intense light exposures separated by long periods of relative darkness, a temporal structure that resembles flickering rather than the smooth gradients that biology expects. Research examining the dose-response relationship between morning light exposure and circadian entrainment has revealed specific thresholds that must be met to achieve robust synchronization. A study published in the Journal of Biological Rhythms demonstrated that mammals require a minimum of 10,000 lux for at least 20 minutes to produce maximal phase shifting of the circadian clock. For context, a typical overcast morning provides approximately 15,000 lux, while a clear sunny morning can deliver 50,000 lux or more. Indoor lighting, even near windows, rarely exceeds 1,000 lux and typically provides only 200 to 300 lux in most rooms. This means that Boni spending the morning hours inside is operating in an environment that provides perhaps 5% of the light intensity their circadian system evolved to expect. The timing of this morning light exposure is as critical as its intensity. The circadian system is not equally responsive to light throughout the entire day. It follows what researchers call a phase response curve, where light exposure at different times produces different effects on clock timing. Light encountered in the biological morning, the hours after the core body temperature minimum, which typically occurs in the pre-dawn period, advances the circadian phase, effectively telling the clock that morning has arrived and pulling all downstream rhythms earlier. Light encountered in the biological evening delays the phase, pushing rhythms later. Light in the middle of the subjective day has relatively little effect on clock timing, though it still suppresses melatonin if levels happen to be elevated. For a dog whose circadian system has been running on a delayed schedule due to chronic evening light exposure, morning light becomes a corrective intervention rather than simple maintenance. The goal is to deliver a strong advance signal that progressively pulls the entire circadian phase earlier until melatonin onset, cortisol rhythms, body temperature patterns, and sleep propensity align with appropriate timing relative to the actual solar day. This correction does not happen instantaneously. The circadian system can typically shift by only 1 to 2 hours per day maximum, meaning that a dog whose rhythms are 4 hours delayed will require several days of consistent morning light exposure to fully resynchronize. The practical implementation of this morning protocol begins the moment Boni wakes, rather than a brief trip to the backyard followed by breakfast indoors. The optimal pattern involves taking your dog outside within 30 minutes of their natural wake time and remaining outdoors for a minimum of 20 minutes of continuous exposure. The location matters less than the light intensity. A walk through the neighborhood provides the same circadian benefit as stationary time in the backyard, provided that the exposure is genuinely outdoor and not filtered through windows or shade structures. Glass blocks a substantial portion of the ultraviolet spectrum and can reduce overall intensity by 50% or more, making window-adjacent indoor time an inadequate substitute for true outdoor exposure. The mechanism through which this morning light bath resets the circadian clock involves immediate changes at the cellular level within the suprachiasmatic nucleus. When bright light strikes the melanopsin-containing retinal ganglion cells in the morning, the signal transmitted to the suprachiasmatic nucleus triggers the rapid expression of immediate early genes, particularly CFOS and PER1, within master clock neurons. These genes initiate a molecular cascade that effectively resets the phase of the cellular clock, synchronizing it to the environmental light-dark cycle. Within hours, this central resetting propagates throughout the body as the suprachiasmatic nucleus sends updated timing signals to peripheral clocks in other organs via neural connections and hormonal messengers. One of the most critical outputs of this morning light exposure is the precisely timed cortisol awakening response. Under properly entrained conditions, cortisol levels surge within 30 minutes of morning light exposure, rising rapidly from the nighttime low to create a sharp peak that promotes alertness, mobilizes energy stores, and initiates the metabolic shift from nighttime conservation to daytime expenditure. Studies measuring cortisol patterns in dogs have shown that this morning rise is both light-dependent and phase-dependent. It requires adequate light intensity to be triggered robustly, and it must occur at the appropriate circadian phase to be effective. Dogs kept in dim morning conditions or exposed to light at irregular times show flattened cortisol curves that lack the sharp morning peak, resulting in sluggish morning energy and reduced daytime alertness. The cortisol awakening response also plays a crucial role in terminating melatonin production. While the primary driver of falling melatonin levels is the light signal itself transmitted from the retina to the pineal gland, Cortisol provides a reinforcing hormonal message that ensures melatonin secretion stops completely rather than tapering gradually. This creates a clean transition from night to day physiology rather than a prolonged twilight state. For Boni, the practical manifestation of a robust cortisol awakening response is clear-headed morning alertness, ready engagement with the environment, and sustained energy throughout the morning hours rather than grogginess that persists well into the day. Beyond the immediate hormonal effects, morning light exposure has profound consequences for evening melatonin timing through a phenomenon researchers call the melatonin gate. The circadian system uses the timing of morning light exposure to calculate when evening melatonin production should begin, typically initiating secretion approximately 14 to 16 hours after the morning light signal in dogs. This means that consistent morning light exposure at 7 creates a biological expectation for melatonin onset around 9 or 10 in the evening. Perfectly timed to support a reasonable sleep schedule. A regular morning light, sometimes at 6, sometimes at 9, sometimes barely present at all, prevents the establishment of this predictable relationship and leaves the melatonin system unable to determine appropriate onset timing. The secondary benefit of extended morning outdoor time involves physical activity, though not in the way most people assume. The goal is not intense exercise that exhausts Boni, which can actually be counterproductive if it leads to daytime napping that dissipates homeostatic sleep pressure. Rather, the objective is gentle, sustained activity, walking, exploring, sniffing, that maintains wakefulness and prevents the dog from immediately returning to sleep after the initial wake period. This consolidated wakefulness from morning light exposure onward helps build sleep pressure that will make evening sleep onset easier and deeper. Wild canids did not wake at dawn only to immediately nap again. For several hours they transitioned into active foraging and social behavior that maintained wakefulness throughout the daylight period. For owners whose schedules make extended morning outdoor time challenging, the intervention can be front-loaded toward the most critical period, the first 30 minutes after waking. Even 20 minutes of bright outdoor light exposure immediately upon waking provides substantial circadian benefit. Far more than an hour of indoor time in typical household lighting. The relationship is not linear. The first minutes of bright morning light deliver disproportionate benefit compared to additional time later in the morning. This means that rearranging the morning routine to prioritize this outdoor window, before coffee, before breakfast preparation, before checking devices, can accomplish the necessary circadian reset without requiring wholesale lifestyle changes. The question of weather and seasonal variation requires addressing directly. Cloud cover, rain, and winter's reduced day length do not eliminate the circadian benefit of morning outdoor time, though they do reduce the absolute light intensity reaching Boni's eyes. A heavily overcast morning might provide only 5 to 7,000 lux compared to 50,000 on a clear day. But this is still 10 to 20 times greater than indoor lighting and remains sufficient for meaningful circadian entrainment. Studies of circadian function in high-latitude regions, where winter days are extremely short and often heavily overcast, show that mammals maintain reasonably robust rhythms, as long as they receive consistent outdoor exposure during whatever daylight hours are available. The key is consistency and maximizing exposure duration to compensate for reduced intensity. The transformation that occurs when this morning protocol is implemented consistently produces changes that are both measurable and observable within days. Owners report that Boni seems more alert and engaged in morning activities, less inclined toward mid-morning napping, and noticeably more ready to settle in the evening. These subjective observations align with objective measurements showing earlier melatonin onset, more robust cortisol awakening responses, and improved sleep efficiency. The percentage of time in bed actually spent asleep rather than in restless wakefulness. The mechanism is straightforward. You are finally providing the environmental signal that Boni's circadian system has been desperately seeking, a clear, unambiguous indication of when morning occurs that allows the entire temporal architecture of physiology to organize itself appropriately. The morning light bath is not an optional enhancement to be implemented if convenient. It is the foundational intervention upon which all other circadian optimization depends. Without proper morning light exposure, attempts to manage evening light become far less effective. Because the circadian system lacks a strong anchor point around which to organize itself. The suprachiasmatic nucleus requires both a clear morning signal that says, "Day begins now," and an evening absence of light that says, "Night is approaching," to maintain robust entrainment. Providing only one without the other leaves the system partially synchronized at best, still vulnerable to drift and disruption. The morning protocol establishes the reference point that makes everything else possible. It sets the timer that determines when evening melatonin will rise, when body temperature will fall, when sleep pressure will peak, and when the following morning's awakening will occur. Master this morning intervention, and you have secured the single most powerful lever for transforming Boni's sleep health and long-term vitality. The evening hours in your home are actively destroying what the morning light exposure built. Every LED fixture, every television screen, every tablet and smartphone contributes to a cumulative blue light burden that systematically dismantles the circadian organization established by dawn. The challenge is not simply to reduce light intensity as evening approaches, though that matters, but to fundamentally transform the spectral composition of artificial lighting so that it stops mimicking the biological signature of midday sun. This requires understanding that not all light is equivalent in its circadian effects, and that strategic manipulation of wavelength can allow adequate illumination for human activities while preserving Boni's melatonin production. The physics of this problem begins with understanding how modern lighting produces white light. LED bulbs generate illumination using a blue LED chip coated with phosphors that convert some of the blue light into longer wavelengths. The resulting spectrum contains a large spike in the blue region, around 450 to 480 nanometers, precisely the range where melanopsin photoreceptors show maximum sensitivity. Manufacturers market these bulbs as daylight or cool white, because the color temperature, measured in Kelvin, approximates natural daylight at 5,000 to 6,000 Kelvin. What they fail to mention is that this spectral similarity to daylight makes these bulbs extraordinarily effective at suppressing melatonin when used during evening hours. Exactly when melatonin production should be ramping up, the solution involves transitioning to lighting sources that provide illumination, primarily through longer wavelengths in the amber to red portion of the spectrum. Bulbs marketed as warm white or soft white, typically rated at 2700 to 3000 Kelvin, contain substantially less blue energy than their daylight counterparts. Though many still emit enough blue wavelength light to cause measurable melatonin suppression, the most effective options are specialized amber or red spectrum bulbs designed explicitly for circadian health, which produce light almost entirely above 550 nanometers where melanopsin sensitivity is minimal. These bulbs provide perfectly adequate illumination for most household activities, reading, cooking, and conversation, while producing negligible circadian disruption even at relatively high intensities. The implementation of this spectral transition should follow the natural pattern of sunset, a gradual shift rather than an abrupt change. Beginning approximately 3 hours before Boni's target sleep time, the transition protocol involves systematically replacing blue-enriched lighting with amber alternatives throughout the spaces where your dog spends evening hours. This does not require rewiring or complex installations. Most households can achieve this through simple bulb replacement and the strategic use of dimmers to reduce overall intensity as the evening progresses. The goal is to create an indoor twilight that mimics the spectral and intensity changes that occur naturally as the sun descends toward the horizon. Smart home systems offer particular advantages for implementing these transitions automatically. Programmable lighting can be configured to shift color, temperature, and intensity on schedules that align with sunset timing, which varies across the year in most locations. A system might maintain standard lighting until 6 in the evening during winter months when sunset occurs early. Then begin a gradual transition to amber spectrum over 30 minutes, followed by a further dimming over the subsequent 2 hours. During summer, when sunset occurs late, the same transition shifts to begin at 8 or 9. This automation ensures consistency regardless of human memory or motivation, removing the need for manual intervention while maintaining the precise timing that circadian entrainment requires. The television presents a particular challenge given its size and brightness relative to other household light sources. Modern television displays use LED backlighting that produces substantial blue light emission, and the content itself often contains bright blue elements in sky scenes, water, and digital graphics. Research measuring light exposure from television viewing has found that a person sitting 3 meters from a large television can receive 100 to 200 lux of blue-enriched light directly to the eyes, an exposure sufficient to suppress melatonin by 30 to 50%. For Boni, lying on the floor or furniture with a direct line of sight to the screen, the exposure may be even greater depending on viewing angle and proximity. Several mitigation strategies can reduce the circadian impact of television viewing without eliminating it. Many televisions manufactured after 2024 include settings variously labeled as night mode, warm color, or reduced blue light that shift the display's color temperature toward amber. These settings reduce blue emission by 20 to 40% while maintaining reasonable image quality for most content. Physical barriers can also help, positioning Boni's evening resting spots so that they face away from the television or are separated by furniture that blocks direct screen viewing reduces their exposure substantially. For households where evening television is non-negotiable, combining these approaches with earlier timing, finishing viewing by 8 rather than continuing until 10 or 11, allows some recovery time before sleep. Personal devices, smartphones and tablets, deserve special attention given their typical viewing distance and the intensity of their backlighting. A tablet held at 40 centimeters from the face delivers far more light to the retinas than a television 3 meters away, despite its smaller size. Because light intensity follows an inverse square law, where doubling the distance reduces intensity by 75%. All major device platforms now include night shift or blue light filter features that can be scheduled to activate automatically in evening hours. These features typically shift the display toward the amber spectrum and reduce brightness, achieving measurable reductions in melatonin suppression. According to research published in lighting and chronobiology journals, the often overlooked source of evening blue light exposure involves ambient sources that seem insignificant individually, but accumulate to create substantial circadian disruption. Digital clock displays, appliance indicator lights, charging status LEDs, under cabinet lighting, nightlights in hallways and bathrooms. Each contribute a small amount of blue wavelength light that reaches Boni's photoreceptors. An audit of a typical modern home might reveal 20 to 30 such sources, many of which operate continuously throughout the night. The solution involves systematic replacement or modification, switching to amber or red LED alternatives where possible, covering displays with amber filters, and eliminating sources that serve no essential function during nighttime hours. The concept of the blackout sleeping zone addresses the final hours before and during sleep, when even amber light can become problematic at sufficient intensity, while amber spectrum light produces minimal melatonin suppression. It still provides a signal of environmental brightness that can interfere with the deepest stages of sleep if intense enough. Research examining sleep quality under different nighttime lighting conditions has found that complete darkness produces significantly better sleep architecture than dim lighting, even when that lighting is spectrally optimized. The practical implication is that Boni's primary sleeping area should be capable of achieving near total darkness, either through heavy curtains that block external light sources or by locating the sleeping area in an interior room away from windows and ambient light. The transition to the blackout zone should be gradual rather than abrupt to avoid creating anxiety around bedtime. Beginning with the amber-lit evening environment, lighting is progressively dimmed over 30 to 40 minutes as Boni's typical sleep time approaches. This gradual reduction allows the dog's eyes to adapt and prevents the disorientation that sudden darkness can produce. By the time full darkness is achieved, Boni should already be drowsy from rising melatonin and homeostatic sleep pressure, making the transition to sleep smooth and natural. Some dogs benefit from a very dim red nightlight, providing just enough illumination to prevent complete disorientation if they wake during the night while producing negligible circadian disruption. The question of human needs versus canine needs requires honest acknowledgement. The lighting protocols optimal for Boni's circadian health involve compromises that some household members may initially find uncomfortable. Amber lighting can make color discrimination more difficult and may feel less bright than the blue-white lighting many people have become accustomed to. Reading small print becomes slightly more challenging under low-intensity amber light. The practical resolution involves strategic spatial separation and individual adaptation. Spaces where humans need bright task lighting for detailed work can maintain standard lighting, while areas where Boni spends evening time transition to amber. Humans adapt to amber lighting within days as their eyes adjust, and many people report that they actually prefer the warm evening ambiance once acclimated. The measurable outcomes of implementing these lighting protocols become apparent within 1 to 2 weeks of consistent application. The most immediate change involves evening behavior. Boni settles more easily as bedtime approaches, showing less restlessness and seeking out their sleeping area voluntarily rather than requiring repeated cueing. Sleep latency, the time between settling down and actually falling asleep, decreases from 20 or 30 minutes to 5 or 10. Nighttime waking frequency drops, with many dogs transitioning from waking 2 or 3 times per night to sleeping through with no interruptions. These behavioral changes reflect the underlying restoration of proper melatonin timing, as measured by saliva or blood samples showing melatonin onset occurring 2 to 3 hours earlier than baseline. The longer-term benefits accumulate across weeks and months as chronic circadian alignment produces systemic improvements. Morning alertness becomes more consistent, no longer requiring extended time for Boni to fully wake and engage. Daytime energy levels stabilize, eliminating the afternoon crashes that suggest inadequate restorative sleep the previous night. Training performance improves as REM sleep properly consolidates learned behaviors into long-term memory. Temperament becomes more stable, with reduced reactivity to stressors and faster recovery when upset. These are not placebo effects or wishful observation. They are the predictable outcomes of providing an organism with the environmental conditions that its biology requires to function optimally. The investment required to implement these lighting changes is modest relative to the health benefits they produce. Quality amber spectrum bulbs cost slightly more than standard LEDs but last for years. Smart lighting systems represent a larger initial expense but eliminate the need for ongoing manual intervention. Physical modifications like blackout curtains are one-time purchases. None of these interventions requires ongoing costs or maintenance beyond occasional bulb replacement. Compare this to the veterinary expenses associated with managing behavioral problems, anxiety medications, or age-related cognitive decline. All conditions that proper circadian function can prevent or delay, and the economic value becomes clear. Even before considering the welfare benefits to Boni and quality of life improvements for the entire household. The transformation of your home's lighting environment from a circadian disruptor to a circadian supporter represents the completion of the environmental foundation necessary for optimal canine health. Combined with robust morning light exposure, these evening protocols provide the clear temporal signals that allow Boni's suprachiasmatic nucleus to maintain precise synchronization with the solar day. The result is a dog whose internal biology is finally aligned with their external environment, whose melatonin rises when it should, whose cortisol peaks appropriately, whose body temperature follows proper circadian patterns, and whose sleep architecture unfolds with the depth and timing that evolution designed. This is not forcing Boni's biology into an unnatural pattern, but rather removing the artificial disruptions that prevented their natural patterns from expressing themselves properly. The transformation happening inside Boni's body as circadian alignment is restored cannot be seen directly, but it can be measured with precision that would have seemed impossible just a decade ago. Wearable technology designed specifically for canine health monitoring has evolved from simple activity counters to sophisticated devices capable of tracking heart rate variability, sleep stages, body temperature fluctuations, and movement patterns with research-grade accuracy. These devices transform subjective impressions into objective data, allowing you to document the physiological changes occurring as morning light exposure and evening light management rebuild proper circadian organization. Heart rate variability represents one of the most sensitive markers of autonomic nervous system function and overall physiological resilience. The term refers not to average heart rate but to the beat-to-beat variation in the intervals between heartbeats, a parameter that reflects the dynamic balance between sympathetic nervous system activation, which increases heart rate and promotes arousal, and parasympathetic nervous system activation, which decreases heart rate and promotes rest and recovery. High heart rate variability indicates a flexible, responsive system capable of adapting to changing demands. Low heart rate variability suggests a rigid system locked in sympathetic overdrive, associated with chronic stress, poor recovery, and increased disease risk across mammalian species. Research examining heart rate variability in dogs has revealed strong circadian patterns, with variability typically highest during sleep and lowest during active waking hours. This pattern reflects appropriate autonomic balance, sympathetic dominance during activity, when arousal and energy mobilization are needed, and parasympathetic dominance during rest when recovery processes can proceed. Dogs with disrupted circadian rhythms show flattened heart rate variability patterns that lack this clear day-night difference, remaining in a state of elevated sympathetic tone even during sleep. Studies correlating heart rate variability with health outcomes have found that dogs with higher sleep time variability show better stress resilience, improved immune function, and lower rates of cardiovascular problems as they age. The wearable devices that measure these parameters attach to Boni's collar or harness and operate continuously, collecting data that is transmitted to smartphone applications for analysis. Within the first week of implementing proper lighting protocols, the data typically shows subtle but measurable increases in nighttime heart rate variability, reflecting the beginning of restored parasympathetic function during sleep. By 2 weeks, the day-night difference in variability becomes more pronounced, indicating clearer separation between active and resting physiology. After 4 to 6 weeks of consistent circadian alignment, many dogs show heart rate variability metrics that have improved by 20 to 40% compared to baseline, a change that corresponds to significantly enhanced physiological resilience. Sleep stage analysis provides another window into the quality of restoration occurring each night. Advanced wearable devices use algorithms that combine heart rate patterns, movement data, and in some cases, body temperature to estimate time spent in different sleep stages. While not as precise as polysomnography with direct brainwave monitoring, these estimates achieve reasonable accuracy for distinguishing between waking, light sleep, deep slow-wave sleep, and REM sleep. The data reveals patterns that owners cannot observe directly, such as the number of complete sleep cycles achieved per night, the total duration of deep sleep, and the timing of REM periods. Dogs with disrupted circadian rhythms typically show fragmented sleep architecture characterized by frequent transitions between stages, abbreviated deep sleep periods, and REM sleep that occurs at inappropriate times or fails to reach sufficient duration. The sleep efficiency metric, calculated as the percentage of time in bed actually spent asleep versus time spent in restless wakefulness, often falls below 70 or 75% in circadian disrupted dogs compared to 85 to 90% in well-entrained animals. After implementing morning light exposure and evening light management, the data documents progressive normalization of these patterns. Deep sleep duration increases, often by 30 to 50%, within 2 weeks. REM sleep consolidates into longer, less fragmented periods primarily occurring in the late night and early morning hours. Sleep efficiency climbs as nighttime waking decreases. The behavioral changes that accompany these physiological improvements become apparent to anyone who interacts regularly with Boni. The dog who previously seemed perpetually tired despite sleeping many hours per day now displays sustained alertness and engagement during waking hours. This paradox, sleeping more total hours yet seeming exhausted versus sleeping fewer, but higher quality hours and appearing energized, reflects the difference between fragmented low-efficiency sleep and consolidated restorative sleep. Training sessions reveal improved focus and faster learning as properly timed REM sleep consolidates new information effectively. Commands that previously required dozens of repetitions to achieve reliability now solidify after far fewer practice sessions. Emotional regulation shows marked improvement as circadian alignment restores proper function to brain regions involved in stress response and emotional processing. The amygdala, which generates fear and anxiety reactions, operates differently depending on circadian phase and sleep quality. Research has shown that REM sleep deprivation or disruption leads to amygdala hyperactivity and reduced connectivity with prefrontal cortex regions that normally modulate emotional responses. Dogs whose REM sleep has been chronically fragmented by circadian disruption often display heightened reactivity, difficulty calming after arousal, and generalized anxiety that seems disproportionate to environmental triggers. As proper sleep architecture is restored through lighting interventions, owners consistently report that Boni seems more emotionally stable and resilient. Separation anxiety, when present, typically decreases in severity as the dog's baseline stress physiology improves. Noise sensitivity and reactivity to unfamiliar people or dogs often diminish as the chronically elevated sympathetic tone resolves. These changes do not represent training improvements or behavior modification in the traditional sense. They reflect normalized neurological function that was being undermined by sleep disruption. The dog's temperament has not fundamentally changed. The obstacles preventing their natural temperament from expressing itself have been removed. The long-term trajectory of health in dogs with properly aligned circadian rhythms versus those with chronic disruption diverges increasingly as years pass. While the immediate benefits appear within weeks, the cumulative advantages of consistent high-quality sleep and proper circadian organization compound across the lifespan. Research examining aging in laboratory animals has demonstrated that circadian disruption accelerates virtually every marker of biological aging, including cognitive decline, immune system deterioration, increased inflammation, reduced stress resilience, and earlier onset of age-related diseases. Conversely, animals maintained under optimal light-dark cycles that preserve robust circadian rhythms show delayed aging across these same parameters. Cognitive function in senior dogs provides perhaps the clearest example of these long-term effects. Canine cognitive dysfunction syndrome, the dog equivalent of dementia, affects a substantial percentage of dogs over 10 years old and manifests as disorientation, altered sleep-wake cycles, loss of house training, reduced social interaction, and decreased awareness of surroundings. The condition reflects progressive neurodegeneration in brain regions, including the hippocampus and frontal cortex, areas critical for memory and executive function. Research has established that sleep quality, particularly deep slow-wave sleep, plays an essential role in clearing the beta-amyloid proteins that accumulate in the brain and contribute to cognitive decline. Dogs maintained on proper circadian schedules throughout their adult lives accumulate less of this pathological protein because their glymphatic system, the brain's waste clearance mechanism that operates primarily during deep sleep, functions optimally night after night for years. The dog that begins circadian optimization at 2 or 3 years old and maintains it consistently may reach 10 or 12 years old with cognitive function that would be exceptional for their age, not because they possess unusual genetics, but because their brain has been provided the environmental conditions necessary for proper maintenance. This is preventative medicine at its most fundamental level, supporting the biological processes that naturally resist disease rather than intervening after pathology has developed. The immune system benefits similarly from sustained circadian alignment over the years. Immune function shows pronounced circadian rhythms in virtually all components, from the trafficking patterns of immune cells through the body to the production of antibodies in response to vaccination. These rhythms evolved to anticipate the daily patterns of pathogen exposure that ancestral animals experienced, with certain immune functions ramping up during the active period, when exposure risk was highest, and others dominating during the rest period when inflammation could be safely deployed for tissue repair. Chronic circadian disruption desynchronizes these patterns, creating temporal chaos, where immune responses occur at inappropriate times or fail to occur when needed. Longitudinal studies tracking dogs over multiple years have found that animals with better circadian regularity, assessed through consistent activity patterns and robust rest-activity rhythms, show lower incidence of infections, faster wound healing, and better responses to vaccinations compared to dogs with irregular patterns. The mechanism involves both direct effects of proper sleep on immune cell function and indirect effects mediated by cortisol and melatonin, whose immunomodulatory actions depend critically on occurring with appropriate timing and amplitude. A dog whose circadian rhythms remain well organized throughout their life maintains immune competence into old age, which allows them to resist infections and recover from illness with the vigor of a younger animal. Metabolic health represents another domain where the long-term benefits of circadian alignment manifest clearly. The epidemic of obesity in pet dogs, affecting over half of all dogs in developed countries according to recent estimates, reflects multiple factors, including overfeeding and insufficient exercise. However, circadian disruption contributes substantially to weight management difficulties even when food intake and activity levels are apparently controlled. Metabolism is not a constant process but rather a collection of time-dependent biochemical pathways that must occur in proper sequence for optimal function. Nutrient processing, fat storage and mobilization, insulin sensitivity, and hunger signaling all follow circadian patterns that become disrupted when the master clock receives incorrect environmental information. Dogs fed the same diet and provided the same exercise but housed under different lighting conditions show measurably different metabolic outcomes. Those kept under natural light-dark cycles with proper circadian alignment maintain leaner body composition, better glucose regulation, and more efficient energy utilization compared to those experiencing disrupted light exposure despite identical caloric intake. The difference lies in when and how efficiently nutrients are processed, with properly entrained animals showing metabolic flexibility that allows them to switch effectively between fed and fasted states, while circadian disrupted animals struggle with this transition and tend toward progressive fat accumulation. Implementing circadian optimization as a lifelong practice rather than a short-term intervention requires establishing it as a foundational element of Boni's daily routine, as automatic and non-negotiable as providing food and water. The morning light exposure becomes the priority upon waking, preceding coffee, email checking, or any other morning activities. The evening lighting transition occurs on schedule regardless of other household activities, with smart systems removing the need for conscious implementation. This consistency is critical because the circadian system responds to average patterns over time. Occasional deviations are well tolerated, but chronic inconsistency prevents robust entrainment from ever developing. The concept of circadian hygiene, analogous to dental hygiene or nutritional discipline, provides a useful framework for understanding this long-term commitment. Just as brushing teeth once does not prevent cavities but daily brushing over years preserves dental health. Providing optimal light exposure on a single day produces minimal benefit, while years of consistent practice profoundly impact health span and longevity. The interventions themselves are simple, even mundane, but their cumulative effects over a dog's lifetime are transformative. The 8-year-old Labrador maintained on proper circadian schedules, since puppyhood looks, acts, and by every measurable physiological parameter is biologically younger than a circadian disrupted 8-year-old, potentially by several years. The return on this investment in time and attention becomes fully apparent only in retrospect, when the 12 or 13-year-old Boni still greets you with enthusiasm each morning, navigates the house without confusion, learns new things readily, and shows none of the profound cognitive decline that has become so common in aged dogs that many owners consider it inevitable. This outcome is not luck or exceptional genetics, though those factors certainly contribute, but rather the logical result of providing an organism with the environmental conditions its biology requires to maintain itself properly across years. The science is unambiguous: circadian rhythms are not optional accessories to physiology, but rather fundamental organizing principles without which biological systems progressively deteriorate. Your role in Boni's long-term vitality centers on this single, controllable environmental variable: the timing, intensity, and spectral composition of light exposure across the 24-hour day. You cannot change your dog's genes. You cannot stop the passage of time. But you can ensure that every day provides the clear environmental signals that allow their circadian system to function as evolution designed. The morning light that streams through your window at dawn. The amber glow that replaces blue-white LEDs in your evening hours. The darkness that envelops their sleeping space at night. These are not lifestyle luxuries but rather biological necessities. They cost almost nothing, require minimal time, demand no special expertise, yet their provision or absence determines whether Boni's years are characterized by vibrant health or gradual decline. The choice, ultimately, is straightforward: align your dog's environment with their biology, and witness the flourishing that results, or maintain modern lighting patterns and accept the shortened health span that chronic circadian disruption produces. The science of canine circadian rhythms provides the knowledge. Implementation requires only the commitment to honor what that science reveals.